Okay, we are continuing on here, chapter 12. Last time we talked about something chemistry-like, I think. We talked about last time how to manipulate equations and the effect of doing so on the equilibrium constant value. So remember that if we were to reverse a reaction, make our products our reactants our products. How that affects K value, once again, is we do take actually 1 over the K value. We don't just change the sign or anything like that. Also, if we need to multiply an equation by a common number, we will actually square, for example, or take the K value to whatever number we multiply by to the power of that. And also, if we need to divide by a common number, we'll actually take the square root in this case of it, but really, whatever we would divide by, we would take the root of that in terms of the K value. So again, sometimes you may have to manipulate some of these equations to add a couple reactions together. And you just want to, kind of like we did in those couple examples, keep track of what you did, and then keep track of what you did to the K value, or need to adjust the K value. Remember as well that when we actually add number of equations together, we actually multiply the K values. That's also, again, something people mess up on. They want to kind of add them together. We do multiply the K values if you are adding a number of individual reactions together. At the end there, we, dare I say, got into the calculation of the season, and that involved ice tables that we started to talk about. And ice tables, again, stands for initial, change, and equilibrium. And we use ice tables, excuse me, we use ice tables to help us figure out what equilibrium concentrations are of everybody in a particular reaction. We can also figure out equilibrium pressures if we're dealing with a KP and pressures through doing an ice table, where initially maybe you're only given the molarity of your reactants. You could safely assume that perhaps you have nothing in your products. In that case, we can assume, like we talked about, that the reaction is heading towards the product side, since there are no products to begin with. And that means the change part here, which is usually represented by X, would mean that our minuses would be there on the left and our pluses would be on the right. The other really important thing that we talked about definitely is this part of the calculation here for the ice table. You also need to take into account coefficients if there happens to be any in the balance equation. So I'll squeeze one here. So if that was like 2C, we would need to put plus 2x in this case. Again, really what that does when you take the coefficients into account, which you should do, otherwise you will get the wrong answer, is it takes into account really the stoichiometry, the mole-to-mole relationship of everybody. So it's a really important part of it. At equilibrium, we typically would just kind of carry everybody down. And at this point, we could go into our equilibrium expression with everybody that's here and solve for X. Once we solve for X, we will then obviously be able to go back into our equilibrium line and get the equilibrium concentrations of everybody by using that X. To solve for that X, it may require simpler math. It may require more complicated math, maybe like the quadratic formula. So we'll talk about a few different ways today to sort of solve these type of problems. The other thing that I skipped over was the other letter that we talked about, which was the reaction quotient, which is also calculated the exact same way that you calculate K. You also, again, take the coefficients as the exponents, just like you do when you write a K expression. We use Q to help us determine a lot of times one of two questions. The first question is usually, are you at equilibrium? And if you're not at equilibrium, which way you need to go to reach equilibrium? Do you need to make more products? Do you need to make more reactants to do so? So if Q is less than K, you're not at equilibrium. You need more products to reach equilibrium. If Q does equal K, then you're at equilibrium. And if Q is greater than K, you're not at equilibrium. you need to make more reactants to reach equilibrium. So we use Q like we did in that sort of problem that we did, which I would sort of classify as just a straightforward Q type question of, are you at equilibrium? If not, which way you need to go to reach equilibrium. The other thing we talked about, I think, towards the end as well is when doing ice tables, sometimes Q should be calculated to verify which way this reaction is heading. If it's not at equilibrium, is it going towards the reactants or the products? Remember, the only way that you can't calculate Q is you have to be given enough information to do so. So you have to be given enough of everybody there, reactants, products, to be able to go into that. The other important thing is typically when we go into an ice table, molarity is sort of the unit there for concentration. And as we talked about, atmospheres is the unit that you want to make sure that you use if you're going into an ice table, if you're doing something with pressure. And by the way, it works the same way as with concentrations. You just do it with pressures. The end result is you get pressures at the end rather than concentrations, but everything in the middle is all the same sort of calculation. And that's also, again, in a situation if you're maybe given pressures in a different unit and they want the answer in a different unit, but you do have to convert everybody to atmospheres, go into the ice table, do the ice table calculation, and then reconvert them at the end to whatever unit you're looking for. Any questions on any of that there? Well, guess we should do it, huh? Well, let's just take a look at one here. All right, so this is where we laid up, and let's take a look at this one together, and we'll do this one together, kind of walk through the different steps here of working a problem like this. I'm gonna give it the old college try and see how we do. All right, so at 1280 degrees Celsius, the equilibrium constant for this guy is lucky number 7. If the initial concentration of Br2 is 0.663, what is the equilibrium concentrations of everybody? So we are going to do an ice table here. We're given the initial concentrations. By the way, this would be a situation where we could not calculate Q because we don't have any product information given to us. So we have no way to calculate that. So we don't have to worry about that. So I personally would start with perhaps the equation. You probably want to make sure it's balanced, which it does look like it is balanced here. We could also start with the equilibrium expression, which means K would equal the concentration of Br, and we would square it because of the coefficient, divided by the concentration of Br2, and that would equal lucky number 7 there, yeah? All right, so initially, the only thing that's given to us here is our Br2. So we do have a concentration there of 0.663. We are not given any information about the Br. So in this case, it is safe to assume that you're starting with nothing in this case. So you can start with 0. This also makes us feel very safe that, is it the forward direction or the reverse direction should be happening in this case? It should be the forward direction since all you got is reactants. So they're going to go one way at this point. So we can feel pretty safe that this reaction should be heading in this direction. And that means that when we get to the change part, this guy should be minuses. So once again, we represent the change with X. So it'll be minus X there. On the product side, it should be increasing with time. We represent that with a plus. And once again, we do need to take this coefficient into account, 2X at this point. Any questions on that so far? All right, so at equilibrium here, we're just going to drop this down, 0.663 minus X and 2X. Any questions on the ice table here? Okay. So the goal here really is to figure out what the changes or the X part of it is. So we're now going to take our equilibrium line and we're going to basically put it in to our equilibrium expression. So we're going to put it in here. And if we do that, we would have 2X and still need to square it, divided by 0.663 minus X would equal 7. Yeah. So now we do a little bit of math. Grab my calculator here and hope for the best. So, go that way. I know I got me 4X squared up on top, right? I need to take this entire thing that's on the bottom and multiply it to the other side, right? So I got to take that entire thing on the bottom and multiply it to the other side. And that's going to give me some numbers, 0.663 times 7. That's going to give me a 4.641 minus 7x. Now remember, we do want to make this like our quadratic, which is kind of where we're heading. So typically what we want to do is move everybody to the same side of the equal and set it equal to 0. It truly doesn't matter which way you go, but most people will keep the x squared positive. Just for some reason, they'll keep it positive. So with that being said, I'm going to take everything on this side and move it to the other side, which means I'm going to subtract the 4.64 and going to add the 7x. Yeah. And that's going to give me an equation that looks something like 4x squared plus 7x minus 4.641 is equal to 0. Questions on that there? Now, this is our quadratic, right? And this represents our A, B, and C. And by the way, you do take the negative with that C, right? So that's going to go into our x is equal to minus b plus or minus a little square root action of b squared minus 4ac divided by 2a. All right. Any questions on that so far? All right, so I'm going to throw some numbers in here, see what I get. Maybe I'm going to go to the next page maybe and just recopy it, I think. 4x squared, 7x. So go a little higher here. 4x squared, 7x. I think it's plus though. Yeah. 4.641 minus 4.641 equals 0, I believe. Right. All right, so going into my x is equal to minus b plus or minus r square root, b squared minus 4ac 2a. So putting our numbers in here gets us x is equal to minus 7 plus or minus. Now, if you clean up inside the square root, you're going to take b squared, which is 7 squared, I think, minus 4 times a, which is 4 times c, which is negative 4.641. Inside the square root, before you take the square root, you should end up with like a 123.256, which you will then take the square root of. And you will end up, after you take the square root of it, like 11.10. Yeah. All divided by 2 times a, which is 8. Yeah. I think. No, I'm just kidding. Hopefully. Yeah. All right. So as we talked about last time, this is going to give us 2x values. So we will go positive first, right? And then divide and then subtract. So doing the positive guy, going to do minus 7. Nope. Going to hit minus 7 plus 1110 there. Divided by 8. Going to give me an x value for the positive way of 0.513, we'll talk it, or call it. Minus 7, and then going to subtract 11.10 divided by 2, not divided by 2, divided by 8, divided by 8. R negative 2.263, we'll call it in this case. Any questions on that so far? So if I go back to my ICE table here, BR2, 2BR, initial change equilibrium. We'll just look at the equilibrium line. And at the equilibrium line, we had 0.663 minus x and 2x, I believe. Which number would not be a good number here? The negative number would not be good because these are the x values that we would put back into here. And clearly, if I take 2 times that -2, I'm going to get me a negative concentration, which doesn't work so good for chemistry, huh? So this number is not going to work because when we put it back in, we're going to get a negative number, right? So negative number, unhappy face. Yeah, that's not so good. So by the process of elimination there, I'm going to go with the other number, which is positive, would be our correct X value. And again, this X value that we just solved for is this X and this X. They're the exact same X. By the way, it's that X and that X as well, just in case. So that means that the concentration of Br2 would equal at equilibrium 0.663 molar minus 0.513. And that's going to get me 0.663 minus 0.513, 0.150, I hope. And for my Br at equilibrium, it equals 2x, which means 2 times my X value there. Molar. 2 times 0.153. Going to give me a 1 point, we'll call it 03. Why not? Molar here. And these would be ideally the equilibrium concentrations here of both of our guys in our reaction once it reaches equilibrium. Any questions on that there? So ice table into the quadratic here in this case, because that's the way we have to solve it in this particular example. Gives us 2 X values. Again, one should not make sense. And once again, as we talked about last time, you may get 2 positive numbers, may get 2 negative numbers, may get a positive and a negative number if you use the quadratic formula. But the deal is once you put it back into the equilibrium line, one of those guys should probably lead you to a negative number, and that is not the one to choose. So you do not want to choose that one. You got to have positive concentrations or positive pressures, right? First off, any questions on that calculation? This is a question? Yeah. How did we get the 0.663 for the initial there? It was actually just given to us in the problem. Yeah. So, yep. So it's one of those values in the problem. Other questions? All right. So this is math. Good thing about math is you oftentimes can check if you screwed up, right? How could I check to see if I screwed up? Flip a coin. What did you? Yeah, so at this point, we now have the equilibrium concentrations, right? Which means when I take my equilibrium concentrations and I put it back into my equilibrium expression, it should equal pretty much 7. So if you take those values that we just got and you do something like 1.03 squared divided by 0.150, you should get about 7. Won't be perfect, right, with some rounding and stuff like that, but you should definitely be in the ballpark. If you do that and you got like 120, you probably screwed up somewhere along the way, yeah? So it's a really good idea, especially if you're doing some quadratic. This is a relatively simple quadratic, by the way. And if you're doing a more complicated one, there's a lot of places where you can kind of screw up. So it's a good idea if you have time at the end, pop it back into the equilibrium expression. And again, with rounding, it should be pretty close to the number that you have there. Again, maybe a little bit off, but if it's significantly off, probably something went bad in terms of your calculation. Any questions on that there? All right, this is the calculation, yeah, of the season here. So I did one. I think you should do one. So why don't you do this one? We take a mixture of 0.5 moles of H2 and we react it with 0.5 moles of I2. We pop it in a 1-liter flask. What is the equilibrium concentrations of everybody? If the K value is 54.3, set that ice table up, see what you come up. Okay, let's take a look, see how you're progressing here on this particular one. So we got 0.5 moles of H2, 0.5 moles of I2 in a 1-liter flask. We're looking for everybody's equilibrium concentrations. We can start with our K expression in this case, which would be our products, which would be HI. Once again, we do need to square it because of the coefficient that we see there. That's going to be divided by the concentration of H2 and the concentration of I2, and that's going to equal a 54.3. So clearly, since I need concentrations to go into that, I need concentrations to go into my ice table. I should convert what they gave me into molarity. That's pretty straightforward in this case since we're dividing by 1. So the concentration of H2 would be 0.5 moles over 1 liter, which will give us 0.5 molar for our H2. We would do the same thing for our I2, which actually will come out the same here. 0.5 moles per liter. Once again, you want to make sure in most cases you're in molarity as you go in there, or again, if you're dealing with pressures, you're in atmospheres. Any questions on that so far? All right, at this point, we're ready to go into our ice table and do this. So I'm just going to write on the next page here because I go a little higher, I think. Yeah, I might even borrow that. I don't know. We'll see. Maybe I won't. Yeah, maybe I will. So initially here, we have 0.5 molar of this guy. We got 0.5 molar of this guy. And once again, there's really no mention of HI there in the problem. So also very safely, you could assume that you have nothing going on there. Once again, because we have no products, we could also make a pretty safe assumption that this reaction is also heading that direction to make products, as all we got are reactants in this case. So we're going to do a change. It's going to be minus x because coefficient here is 1, minus x because coefficient here is 1, and we should be gaining products. So that's going to be a plus 2x because the coefficient there is 2. Bringing all this down here to our equilibrium line, 0.5 minus x, 0.5 minus x, and 2x. Any questions on the ice table there? Remember, at this point, the goal is really to solve for what x is equal to. So we're going to use our equilibrium expression, which once again is our HI squared divided by our H2, our I2, and that equals our 54.3. So taking our equilibrium line here and basically putting them into the appropriate spots here, we will put it in and we will get something like 2x squared up on top divided by 0.5 minus x times 0.5 minus x is equal to 54.3. Yeah. So we want to solve this mathematically. And mathematically, we should solve it by, hopefully you can recognize it's a perfect square, perhaps. Yeah, big square root on both sides. Unless you're fond of the quadratic, you can roll quadratic if you like to, but it actually is a perfect square on both sides there. So I'm going to go that route. If you go quadratic, you should get the same, believe it or not. A little longer probably, but you'll get the same answer if you did it. And that will reduce this down to 2x up on top, a 0.5 minus x. And the thing I personally forget to do most of the time is actually take the square root there at 54. So I do that a lot, like, whoops, square root of 54.3. There we go. So I'll remember to do it this time. And we should get 7.36885, we'll call it. Once again, now it's much easier to solve for. We're going to solve for x. We're going to multiply what's on the bottom to the other side. So we're going to bring everybody over there. That's going to give us a 2x is equal to a 3.68443 minus a 7.36885x. At this point, we want to combine our x's to the same side. So I would think it would make sense to add this, right, back over to that side. And that will give us 9.36885x equals 3.68443. Last, we were going to bring that back to the other side by dividing, right? I think that's math wise what we're going to do. And we're going to end up here 9.36885. A X value of 0.393 in this case. Any questions on that there? In this case, that is the X value, right? So no two X values here. So that is going to be our X value. Once again, this X value that we just solved for is the X value here, here, here. It's this X value, that X value, that X value. So we're going to put that X value back into each of those, and that will give us, in terms of the concentration of H2, at equilibrium is 0.5 minus X, which would be this. And that's going to give us 0.107, I think. In this case, our I will be the same. 0.5 minus X. And lastly here, our HI will equal 2 times X, 0.393. And that's going to give us 0.786 molar. And those would be our equilibrium concentrations of these guys. And once again, if you throw it back into your equilibrium expression at this point, you get something like 53.96, which is pretty much like 54. So it seems good. You didn't screw up anywhere along the way. Yeah, it probably won't be in most cases dead on because of some of the rounding that you do. But it should definitely be pretty close. Yeah. I would say if you're getting like 5 or so differences, that's probably getting to the point where maybe something more than rounding or some really bad roundings happening in that case. But it definitely should be in the ballpark. Yeah. But I would say probably in most cases, it may not hit exactly because of the rounding though. Yeah. Other questions? So hopefully you can see a pattern here. Ice table, solve for X. Look for an easier way sometimes, right? Don't always go the hard way. But again, if you like quadratic, and there may be the only way to solve it in certain cases, you got to do quadratic. But you can do quadratic in every situation if you're comfortable doing it and stuff like that. You should, again, get the same answer as what we got here. Well, let's try another one because this is the big day of ice tables. Let's do the same equation, except here we're starting with 0.00623 molar H2, 0.00414 molar I2, 0.0224 molar HI. What is everybody's equilibrium concentrations? This one might take a little longer. So make sure you work through it. I'm going to do it too on the paper right here. See if I remember how. Okay, let's take a look, see how you're doing. This one should get your math skills going, hopefully. I'll just give you a headache, one of the two, I suppose. All right, well, in this one, we're dealing with the same equilibrium. And in this case, we have the concentrations of H2, I2, and HI. So that means that in this case, if you didn't do so, this might be a good place to calculate what? Q, since we do have everybody given to us. So clear this reaction is going. Don't know if we're at equilibrium. I would guess we're not, otherwise it wouldn't be much of a problem. But more importantly, we could check which way this thing needs to go to reach equilibrium. So this would be really like a second situation where you would want to calculate Q just to verify you're probably not at equilibrium, but which way you need to go. Remember that Q is calculated the exact same way as K. So we would take the HI concentration given to us and square it, divided by our H2 and our I2 here, and putting in our numbers, we got 0.0224 squared, divided by our H2 there, which is 0.00623. And our I2 of 0.00, bless you, 414 in this case. And we pop all that in there, a little 19 and change, I think. And we get a Q value here of 19.5, we'll call it. So if we compare our Q to our K in this case, our Q is actually less than our K value, right? So this tells us that we are not at equilibrium, which is probably not much of a surprise since it's kind of an equilibrium problem. But it also tells us, though, to reach equilibrium, which way we need to go. We need to go opposite of where it's pointing, towards the product side. So this way we know for sure when we get to our ice table, we know where our minuses should be, right, and our pluses should be. So again, this would be sort of the second situation where you would want to use Q or the reaction quotient outside of just a direct Q type question. Any questions on that there? All right, now that we got that out of the way, let's just go have some fun with some math, maybe, just to show you I did it myself as well. There you go. All right. So let's start with the equation here, which is our H2 plus our I2 going to our 2HI. Obviously, we could write our equilibrium expression as well, which will look pretty much like our Q expression. And this is going to equal our same 54.3. All right, so we do got numbers everywhere on this one. So we got initially 0.00623, 0.00414. And remember, in this case, this is not 0. We actually do have a number here initially as well, which is, again, why we were able to calculate Q, because we have everybody's information given to us, as opposed to previous problems where we weren't given anything about the product, so there's no way you could possibly calculate Q in that case. Change is going to be pretty similar to what we did last time, minus x, and plus 2x. And once again here, we feel confident about that because we did calculate Q, that we're heading in the right direction. That means when we pull this down, 0.00623 minus x, 0.00414 minus x, 0.0224. And remember, this is actually plus 2x, not minus, so plus on that side. Will screw up your calculation later on if you lay up a minus there, obviously. Any questions on the ice table here? A lot more numbers. So. Same deal is going to happen. We're going to take our equilibrium line basically and put it in here, and then start crying at that point. Probably. Let's take a look. We got 0.0224 plus 2x. That's going to be squared, divided by 0.00623 minus x times 0.00414 minus x, and that's going to equal 54.3. This, unfortunately, is not a perfect square on both sides. So this is factoring, foiling, whatever you do for Thanksgiving. I don't know. There's a method, they call that a math these days. I don't know what they used to call it. But we do have to basically factor out the top and the bottom, right? Before we could actually do the math of it. So I'm going to do that kind of separately. I'm going to do the top part first, just so you can see it. And then I'll do the bottom part so you can see it. And then I'll put it back together. And we'll do the rest of the part of it so you can see it. And we'll go full out on this one here. All right, so I'm just going to start with the top here. All right. And this top on this side, obviously. So on the top here, I basically got 0.00. No, not too many zeros there. Try that again. All right, here I got 0.0224 plus 2x times 0.0224 plus 2x, and foiling, factoring, whatever they call that, again, in and out, right? Sounds good right about now. There you go. So in and out there twice, or just get a double, I suppose. All right. So if you do that, you will end up with, on the top here, we do everything separately, you will end up with something like 0.00050176 plus 0.0448x plus 0.0448x plus 4x squared. We obviously could combine our x's there, and for the top part, we will get a top part of the equation that looks like 4x squared plus 0.0896 x plus 0.000501. I think that's a 26, I think, 76. So that is the sort of equation you should get after you factor everything out. I'm going to do the exact same thing there for our bottom guy, and we're going to get an equation for the bottom there. Any questions first off on that part of it there? Okay, so I'm going to flip the page so I could start at the top. So I know it's hard to see as it gets a little lower here. All right, everybody good for now? Yeah. Okay. So what I'm going to do now is the bottom part. So I'm going to factor out these two guys here on the bottom next. So let's take a look what that looks like. So on the bottom there, we had 0.00623 minus x times 0.00414 minus x. Once again, a little in and out action there, right? And if you do that, you will get for the bottom 0.0000. I guess I could use a little scientific notation there, but oh well. 25792 minus 0.00623x minus 0.00414x plus an x squared. Once again, here I'm going to combine the two x's to give me one equation for the bottom, which will look like this, I think. X squared minus 0.01037x plus 0.000025792. Any questions on that there? All right, so I got both of my equations there on the left. I'm going to put them back in to do a little bit more stuff here. So again, for the top equation, we ended up with this on the previous slide, 4x squared plus 0.0896x plus 0.000500176 divided by what we got up there, x squared minus 0.01037x plus 0.000025792, and that's going to equal our K value of 54.3. So again, that's just the middle work there of all the factoring, so you can see it. Any questions on any of that? All right, a little bit more math to go. I pretty much need to take what's on the bottom, this entire thing here on the bottom, and multiply it to the other side, right? And if I do that carefully, the stuff on the top will not change. So 4x squared plus 0.0896x plus 0.00050176 equals, so I'm going to multiply everything I got on the bottom to the other side, gives me 54.3x squared minus 0.56391x and 0.0014005. And again, all I did is take what's on the bottom to the other side. We're almost there. We're now going to combine everybody. So once again, most people will keep that x squared positive. So I'm going to take everything on the left-hand side here and just send it over to the right-hand side, yeah? So basically, I'm going to take everything here and bring it over here to combine it to finally give us the equation that we need. And if you do that, you're going to subtract the 4x squared. You're going to subtract the 0.0896, and you're going to subtract the 0.000500176 to the other side. Gives you 50.3x squared minus 0.652691x plus 0.0008987 equals 0. dare I say, we have our A, B, and C finally through our stuff. So clearly here, we want to be careful as we kind of move around. We position things, don't add zeros, lose zeros, have to scratch out your paper like me. You know, you don't want to do those things. Yeah. Any questions up until this point? All right, now that we have our equation here, we're ready to go. Building lights this year. We're going to go into our quadratic. And once again, I'm going to flip to the next page so I could kind of write a little bit higher so everybody can hopefully see it. All good? Yeah. Okay. So when we rewrite the equation one more time, 50.3 x squared minus 0.652691x plus 0.0008987 equals 0. All right, so again, that's our A, our B. We do take the negative with it, and our C. And we're going to go into our quadratic. So minus B would be actually positive 0.652691 plus or minus. If you put everything into the quadratic and do what's inside the square root, you will end up with this number 0.245187, which upon taking the square root of, you'll end up with 0.4952. So if you put everything into the quadratic underneath the square root, that's the number you should get. Then a little square root action. That's going to be divided by 2 times A, which is 2 times 50.3, gives us 100.6. Yeah. Now we're ready for our 2x values, I hope. All right, doing the positive we'll go with, I think. So doing the plus will get us 0.0114. And doing the subtraction, the 0.652 minus 0.4952 divided by 100.6 will give us 0.00157, give or take rounding, depending on where you round it. You might have slightly different, depending if you round it a little bit more than I did. Any questions up to that point? All right, so these are our 2 possible x values that we could put back into our equilibrium line, which, by the way, let me just write the equilibrium line here for our H2, our I2, and our HI. So at equilibrium here, we have 0.00623 minus x. For the I, 0.00414 minus x. And we have for the HI 0.0224 plus 2x. So we want to look at these and see which one maybe doesn't make sense. And I'm going to go with this one doesn't make sense. Why does that one not make sense? It is a bigger number than this, right? So when you put it in there, you're going to get a negative number, which is not good, right? So once again, one of those guys are going to give you a negative number when you put it back into the equilibrium line. So this is too big, which means I'm going to go with this as our winner here. So we're going to put this in, and that means for H2 at equilibrium, we should have 0.00623 minus 0.00157 molar. And that's going to give us 0.00466 molar. For our I2, we will have 0.00414 minus x. And we'll use our x value we just solved for. And that will give us 0.00257. And lastly, here for our HI, don't forget we actually had an initial on this guy, right? So 0.0224, and remember it's plus 2 times x, 0.00157. And that's going to give us 0.02554 molar. And there it is, yeah. 3 pages, 1 page. question on any of those? If you put those numbers back in, I really hope it's 54. I think it is, I think. So if you do put these numbers back into our equilibrium expression, we take 0.02554 and square it, divided by 0.00257 and divided by 0.00466, 54.5, basically 54.46. Feels pretty good. Any questions on any of those steps? So this would be a more complicated, yes, quadratic one. The key here is just to kind of keep track of everything. Don't lose any zeros along the way, put things back together. This is also why it's important at the end, right? To check yourself. Also important that you can know you screw something up. Like if you get to this part inside and you get a negative number, yeah, you screwed something up. Which is a scratch out right here. I screwed something up and I had to go back and fix it. So these are things you want to think about along the way. Don't get frustrated if you get a negative number at that point. Just know you probably messed up somewhere, adding something together or something at that point. Any questions? Happens to me as well. Yeah. You cannot. We'll talk about why that is in the next example and what that is in the next example. Okay, so let's take a look at this one since we're getting to the end here, just to talk about a couple of things. This one might look a little different as you're going through your ice table or afterwards, but we'll just start the same way. We do have our Kp given to us in this case, and that means that we could write our Kp expression, which again works the same way as concentration, except that you're dealing with pressures. So this would be the partial pressure squared of NH3 divided by the partial pressure of N2 times the partial pressure cubed of H2, and that equaled 4.31 times 10 to the minus 4. Now that I ran into my equation here, I'll just rewrite it here. So as I mentioned before, it works the same way, regardless if you have concentration or pressures, but again, it does need to be in atmospheres. And in this case, it is in atmospheres, so we're okay. We don't have to do any type of conversion when we go in here. So initially here we have 0.862 pressure, 0.373. And once again, we were not given anything in terms of our product, so we could assume 0. Once again, because we were not given anything in terms of our product, we could also assume that this reaction is obviously going to head towards the product side. Rest of it works the same. It's going to be minus x minus 3x plus 2x in this case. This means that when we pull everybody down here, 0.862 minus x, 0.373 minus 3x, and a 2x that is happening at this point. Just like everything else that we did with concentrations, we're going to take what we have here and go into our expression. And that will give us something that looks like this, I think. 2x squared divided by 0.862 minus x times 0.373 minus 3x. And that's going to equal 4.31 times 10 to the minus 4. We obviously want to solve for x here, and I do need to cube the bottom guy as well, as it is cubed right there. So we do need to solve for x, and clearly we don't want to touch any of that math there, because that does not look like fun, and we just did one that wasn't fun, so we definitely don't want to do that. So we want to think about maybe an alternative way that we can solve for this. So when we look at this K value here, that K value is a large value or a small value? It is a small value, right? And what that means, right, when we have a small value of K is when we reach equilibrium, should we mainly have reactants or products? We should actually have reactants, right? So products over reactants, larger number on the bottom, right, gives us a smaller K value. So we mainly should have reactants when we reach equilibrium, which means in terms of the change here, it's not going to be all that much, right? Because we're going to kind of hang out on the reactant side. Not much is going to go to the product side because the K value is really small. So we can make an assumption, and we could assume in this case, because the K value is small, that x is equal to 0. You clearly cannot get rid of all the x's, otherwise you have nothing to solve for. But the reason we don't get rid of this X is if you're starting with nothing and you make just a little, that's still a lot, right? So there's still a lot if you started with nothing. So we get rid of all the X's that are minus from something, maybe added to something. Those are the X's that we would get rid of, not obviously the guy who started at 0. So that would reduce this down to 2x squared up on top divided by 0.862, 0.373 cubed, and that would equal 4.31 times 10 to the minus 4. Now that looks much better to solve than the previous one that we had going on there. So we are going to solve this. I'm going to clean up the bottom here, and I'm going to get 0.373 cubed times 0.862. That's going to give me a 0.044733. I'm going to multiply that now to the other side. And I'm going to make sure I use my exponent button. I'm going to get basically 4x squared equals 0.00001928. I then need to divide by 4. And then after I do that, I need to take a square root, right? So divide and then take the square root. So I'm going to divide it by 4 and then take the square root. Make sure you hit equals somewhere in there. And that's going to give us an x value, if you do that, of 0.00220, basically. Any questions on that? So once again, lastly here, I divided by 4 and took the square root. All right, so to your question, we need to check our assumptions if we make our assumptions to make sure that it is good. And the way that we check our assumptions in this class is, as the question was asked, what is sometimes referred to as the 5% rule, which means the way that you check your assumption is you take the X value that you just got, which in our case, our X value was 0.00220, and you divide it by what you were going to subtract it from. So you divide it by that number, divide it by that number. Frankly, if you do one of them and you're good, you're probably good on both of them. So I'm going to divide it by the 0.862, times it by 100%. And if I take that divided by 0.862 times it by 100%, I end up with 0.25%. That is less than 5%. Then you put a happy face and move on with your life, yes? Now, if it happens to be higher than 5% or 5% or higher, you got to go back and find another way to solve that. Probably in our case, that would be the quadratic formula you would go back to solve it for. But that is what you do. You could also check it with the other one. You could take 0.373 divided by, 3 times our X value divided by 0.373 and times by 100. Like I said before, if one works, usually they're both good. You don't usually have to check them both. All right, so since we did check it and it's good, we now have the proper X value to put into here. And let's do that. So for the pressure here of N2, we would take 0.862 minus our X value. And that will give us a 860 atmospheres. Remember, these are pressures, not concentrations. For our partial pressure of our H2, again, we will put it back into here. 0.373 minus 3 times 0.0022. Going to give us a 0.366 atmospheres. And lastly, we're going to put it back into here, which would be our partial pressure of NH3. And that would be 2 times 0.0022. And that's going to give us 0.0044 atmospheres. And these would be our equilibrium partial pressures. Now, a couple of things to fully answer your question before we wrap it up here for today. The question was earlier, why did we not, or why could you not use the 5% rule or the assumption on the previous problems? Why could we not do it on the previous problems? The K value for our very first one was 7, which is a large value, which means you mainly have products and you have a pretty big change. The other two that we did, the K value was 54.3, which is also considered a large value, which means you should have a pretty big change that's occurring. So you could only use the assumption if your K value is small and it has to be less than 1. Will it work all the time? It will not, which means you should always check it to make sure it works. This is also a situation where, frankly, you just want to roll with the quadratic and not worry about the assumption. You could do that. It will probably save you some time to do the assumption. And you'll find out pretty quickly it doesn't work. So it's probably a good idea to do it in the situations where you can do it. But you don't necessarily have to do the assumption. You can still roll through some other math way to do it. So once again, if it is above 5% or more, we cannot solve it with the assumption. You will have to go back to quadratic formula to solve it. For us, that is the most complicated thing we're going to do is quadratic. We will not do what you will sometimes see in books, which is known as successive approximation, which means you throw a number in there less than what you're subtracting, and you put a number in, solve for x, and you keep doing that until you get the number you put in is the number you get out, which if you're pretty crappy at it, could take an all-day project. So we will not do successive approximation, but you might see it in a textbook, and sometimes they solve problems that way. So we will do the 3 different ways that we just did here today in our big ice table day. Quadratic could be a perfect square, could do an assumption. Those are 3 different ways to solve these problems. You need to know how to do all those ways. Yeah. Any questions on any of that? Yeah. Say it one more time for. Yeah. Yeah. So basically, for the 5% rule to check it, you take whatever x value you get and you divide it by whatever you're going to subtract it from. You could also do it for this guy as well. If you're going to do it for this guy, what you would actually do though is multiply the x value by 3 first and then divide it. And if you do that, I think maybe you get like 2% or something like that on that one. And I say in my experience, usually if you check one of the reactants and it's good,